Hello and welcome to G Fun Facts Online, your go-to source for the most amazing tidbits from the world of science. I'm your host, and today we're diving deep into a realm where fundamental forces of nature, usually considered sworn enemies, are found dancing a bizarre and beautiful quantum tango. We're talking about magnetism and superconductivity. Buckle up, because this is going to bend your mind. All right, so let's set the stage. In one corner, we have superconductivity. Imagine electricity flowing through a wire with absolutely zero resistance. No energy loss, no heat. Pure, unadulterated current. It's an incredible phenomenon that some materials exhibit when cooled to super low temperatures. Electrons, which normally repel each other, team up in what are called Cooper pairs and glide through the material like ghosts, facing no opposition. In the other corner, we have magnetism. Think of your fridge magnets or the Earth's magnetic field. This arises when tiny magnetic moments of electrons within a material all decide to point in the same direction, creating a persistent magnetic field. Simple enough, right? Now, here's the drama. For the longest time, physicists thought these two were like oil and water, cats and dogs, pineapple on pizza for some, you get the idea. They just don't mix. Superconductivity typically gets crushed by strong magnetic fields. The delicate Cooper pairs, especially the conventional ones where electron spins point in opposite directions, are easily torn apart by magnets. Plus, superconductors have this cool party trick called the Meissner effect, where they actively kick out magnetic fields from their interior. So, a material being both a strong magnet and a superconductor seemed impossible. But, as always, the quantum world loves to throw us curveballs. Scientists have been discovering a whole new class of materials, these exotic quantum materials, where magnetism and superconductivity don't just tolerate each other, they can actually coexist and sometimes even cooperate. These are the magnetic superconductors, and they are seriously cool. So how do these materials pull off this seemingly impossible feat? Well, it often boils down to unconventional types of superconductivity. One superstar in this field is something called spin-triplet superconductivity. Remember those Cooper pairs? In this version, the two electrons in a pair have their spins aligned in the same dot direction. These spin-triplet pairs are like the special forces of the electron world, much more robust and can handle magnetic fields like champs. In fact, sometimes magnetism can even help them form. Then there's the wonderfully named FFLO state. That's Folda-Farrell-Larkin-Ovchinnikov state for long. Predicted way back in 1964, this is an exotic state where superconductivity gets a bit crafty in strong magnetic fields. The Cooper pairs gain a bit of momentum, and the strength of the superconductivity actually varies in a wave-like pattern throughout the material. It's like superconductivity is finding clever pathways through the magnetic landscape. Now, perhaps the most surprising poster child for this quantum dance comes from something you probably have in your pencil right now. Graphite. Yes. Good old carbon. MIT physicists, in a discovery slated for May 2025, found a new type of chiral superconductor that is also intrinsically magnetic in a special form of graphite. They took tiny flakes of graphite, just 4 or 5 layers thick, stacked in a specific rhombohedral way. Think of a tiny offset staircase. When cooled down to near absolute zero, these flakes became superconducting. But here's the kicker. They could be switched between two different superconducting states with a magnetic field, like flipping a tiny magnetic switch. This suggests the material has its own internal magnetism while being a superconductor. How wild is that? Apparently, in this specific structure, at supercold temperatures, electrons slow down and interact to form these spin-aligned Cooper pairs that collectively generate magnetism. Who knew pencil lead could be so exotic? And graphite's surprises don't end there. Other research has shown that stacking graphene sheets, single layers of carbon, at specific magic angles, can lead to superconductivity that's incredibly tough against strong magnetic fields, up to 10 Tesla, which is huge. Beyond graphite, there's a whole zoo of these magnetic superconductors. We have uranium-based compounds like uranium ditelluride, or UTE. This material is a prime candidate for spin-triplet superconductivity, and can withstand ridiculously high magnetic fields. It even shows Lazarus superconductivity. You hit it with a strong magnetic field, say 35 Tesla, superconductivity dies, but then you crank the field even higher, between 40 and 65 Tesla, and bam! Superconductivity comes back from the dead. This is a huge clue that something very unconventional is going on. Then there are iron-based superconductors. Discovered in 2008, these materials have been a fantastic playground for studying this interplay. Some of them, like RBUFAAs, show both ferromagnetism and superconductivity. It's thought that in some of these, the magnetism and superconductivity might live in different parts of the material's structure, like friendly neighbors who mostly keep to themselves. We also have heavy fermion superconductors, cuprate high-temperature superconductors, where magnetism is thought to be key to the superconductivity itself, and even organic superconductors where the FFLO state has been observed. So what's the quantum magic that allows this coexistence? We've touched on spin triplet pairing and the FFLO state. Another key player is spin-orbit coupling, a relativistic effect linking an electron's spin to its motion, which can lead to really complex and protective superconducting states. Sometimes, believe it or not, magnetic fluctuations, think of a shimmering, unstable magnetic state, can actually cause superconductivity by helping electrons pair up. It's like the thing that's supposed to be the enemy becomes the matchmaker. Scientists use an impressive toolkit to study these materials. They measure how resistance changes with temperature and magnetic fields, use super-sensitive magnetometers called skewids, blast them with muons and neutrons to see the magnetic structures, and use powerful microscopes like scanning tunneling microscopes to see things at the atomic scale. Now, why all this fuss? What's the payoff? While the applications are potentially revolutionary, first up, quantum computing. Some of these magnetic superconductors, especially spin triplet ones like UTE, might be topological superconductors. These could host exotic particles called Majorana fermions, which are perfect for building fault-tolerant quantum bits, or qubits. This could be a game-changer for making quantum computers stable and powerful. Then there's spintronics, a field aiming to use electron spin for faster, more efficient electronics. Magnetic superconductors, where spin and charge are so intimately linked, are a natural fit for new spintronic devices. And imagine superconductors that don't mind strong magnetic fields. This is crucial for MRI machines, particle accelerators, and even fusion reactors. Magnetic superconductors are, by definition, more resilient. Of course, it's not all smooth sailing. These materials are often rare, complex to make, and many still only superconduct at incredibly low temperatures. Understanding the exact microscopic mechanisms is a huge puzzle, and making these materials pure enough and scalable for real-world devices is a big hurdle. The path forward involves a huge effort in discovering new materials, pushing experimental techniques to their limits, and developing better theories. The graphite discovery is exciting because it suggests these amazing properties might be found in simpler, more common materials than we thought. So magnetic superconductors are truly at the cutting edge of physics. They're challenging our old ideas and showing us just how weird and wonderful the quantum world can be. Each discovery helps us understand matter at its most fundamental level and could pave the way for technologies we can only dream of today. That's all the time we have for today on G Fun Facts Online. I hope you enjoyed this dive into the quantum tango of magnetism and superconductivity. If you did, don't forget to like, subscribe, and hit that notification bell so you don't miss our next exploration into the wonders of science. Until next time, stay curious.